Hello, everyone. Today we're diving into one of the most fascinating topics in physics, the nature of light. We'll trace how great thinkers like Newton, Huygens, and Einstein tried to answer one big question. What exactly is light? Is it a wave, a particle, or could it be both? Let's find out how this mystery evolved through the centuries. Let's start with something fun: lightsabers. You've seen them in Star Wars, glowing beams of energy cutting through the air. But have you ever wondered, are lightsabers made of particles or waves? That question actually connects to one of the biggest mysteries in physics, the true nature of light. To find out what light really is, let's go back to where scientists first started asking the same question. Back in the 1600s, two great minds couldn't agree on what light really is. On one side, we had Isaac Newton, who believed that light was made of tiny particles, or corpuscles. On the other hand, we have Christian Huygens. He argued that light behaves like a wave. It was a real scientific showdown. Newton's fame made his idea more popular for a while, but Huygens wasn't exactly wrong either. So who turned out to be right? Well, the story doesn't end here. Let's see how later discoveries change the game. We'll start in the ancient Greece. We have Plato, who proposed an extramission theory suggesting that vision occurs when light rays emitted from the eyes interact with objects. He said that light is a form of emanation from the observer's eye, which touches the object being observed. Next one is his student Aristotle. He introduced a contrasting view known as intromission. He said that vision occurs when light rays from an object enter the eye. He believed that objects emit form or species that travel through the air to the eye, allowing perception. And here comes Euclid in 300 BC. He is the father of geometry. He supported the extramission theory, and in his work on optics, he described how visual rays emanate from the eye in straight lines and diverge to form a cone shape. During the medieval age, Ibn al-Haytham in 1000 AD, in his work Kitab al-Manazir, or Book of Optics, he rejected both Plato's and Euclid's extramission theories and supported intramission instead. He also conducted experiments demonstrating that light travels in straight lines and studied refraction and diffraction. Ibn al-Haytham is the father of optics. And now, in the scientific revolution, Christian Huygens took a bold step in 1690 when he proposed his wave theory of light. He imagined light moving in waves, kind of like ripples spreading out when you drop a stone into water. He even suggested that these waves travel through an invisible substance called ether, which he thought filled all of space. What's cool is that he also introduced the concept of wave fronts, where every point on a wave can create smaller waves that spread out, and that idea still pops up in modern wave physics today. And then Sir Isaac Newton. Isaac Newton came in with a completely different take. In 1704, he proposed the corpuscular theory of light, saying that light is made up of tiny particles he called corpuscles. According to him, these particles shoot out in straight lines from a source, kind of like a stream of tiny bullets. This idea helped explain why light reflects off surfaces and bends or refracts when it passes through glass or water. Newton even thought that different colors came from corpuscles of different sizes or masses. So for a long time, Newton's idea ruled the scientific world, but eventually, experiments started revealing something that the particle theory couldn't fully explain. About a century later, Thomas Young put Huygens' wave idea to the test with his double-slit experiment in 1801. He passed light through two narrow slits and noticed a pattern of bright and dark bands on a screen. That pattern, called an interference pattern, showed that light waves were overlapping. It means some waves added up, making bright spots while others cancelled each other out, creating dark ones. This was solid proof that light behaves like a wave, not just as tiny particles. When light passed through two slits, instead of seeing two bright spots on the screen corresponding to the slits, Young observed a pattern of bright and dark fringes, and this is called an interference pattern. Same interference may be seen in water waves. Then came James Clerk Maxwell, who tied everything together beautifully. He developed the electromagnetic theory of light, showing that electric and magnetic fields can travel through space as waves. His famous Maxwell's equations describe exactly how these fields move and interact. The amazing part? He discovered that visible light is actually just a small part of a much larger electromagnetic spectrum, and this is made of waves of different wavelengths, all traveling at the same speed. So light was confirmed to be a wave. Case closed, right? Well, not quite. The next discovery brought the particle idea back, and this time with a twist in modern physics. For Einstein, light is a photon. From the works of modern physicists, light is a photon and a wave. And light as Einstein studied, Einstein changed everything again. He explained that light isn't just a wave, it's also made of tiny particles of energy. And we know this already as photons. These photons can knock electrons loose from metal surfaces, which we call the photoelectric effect. Later on, scientists like Louis de Broglie took it further and proposed that not only light, but all matter, even particles like electrons, have both wave and particle properties. This idea is what we now call wave-particle duality. So after centuries of debate, the answer to whether light is a wave or a particle is both. And that's what makes it so fascinating. This is a timeline showing the history of research on light. You may pause this part of this video to study the timeline. Now, since we now know that light has dual nature, let's examine it further or in detail how light has dual nature. Sometimes light behaves like a particle, and we've mentioned that as photon, which explains how light travels in straight lines. Sometimes it behaves like a wave, which explains how light bends or diffracts around an object. If light is a particle, when we look at light as a particle, we see it as tiny packets of energy called photons. Each photon carries energy and momentum, even though it has no mass. That's why light can still push on things or get bent by gravity, like near a black hole. Light also travels in straight lines and can even knock electrons out of metal surfaces, and this is what we call as photoelectric effect, as explained by Albert Einstein. When light is shined through two holes, or just like what Thomas Young did, we see not an interference pattern, but two light beams or beams of light on the screen. And this proves that light is a particle. When light behaves like a wave, as I am showing you in this part of the video, when light behaves like a wave, it spreads out, bends, and interferes, just like ripples on water. This wave nature explains patterns like diffraction, interference, polarization, And according to Maxwell, light is made up of oscillating electric and magnetic fields that travel through space. So when you see colors in a soap bubble or any kind of bubble or in a rainbow, that's light showing off its wave side. This is a table differentiating what property of light is of waves and what property of light is of particles, and what property of light is both a wave and a particle. So, in a nutshell, after centuries of debate and discovery, we've learned that light is both a wave and a particle. It can spread out and interfere like waves, but it also comes in tiny energy packets called photons. This dual nature of light is one of the key ideas that shape modern physics and even led to quantum theory. In the end, light reminds us that nature doesn't always fit into neat categories. In short, it's full of surprises. Now that we've explored light's strange and fascinating nature, let's see how this concept connects to the world of quantum mechanics in the next topic, in the next meeting. But before we go to that topic, I want you to watch the video in this link. Thank you and good day.